All right, nice. Okay. So welcome back. So we're excited to have Gururaj here. He's an incoming assistant professor at the University of Toronto. His research is on hardware and system security with a focus on microarchitectural side channels, rowhammer attacks, and defenses and trusted execution environments. His work regularly appears at computer architecture conferences like ISCA, Micro, HPCA, ASPLOS, and security conferences like IEEE Security and Privacy, Usenix Security, and CCS. His recent work on rowhammer defenses received a Best Paper Award at HPCA this year, 2023. And with that, I'll hand it off to Gururaj.
Thank you, Sagar. Hello, everyone. I'm Gururaj. And today I'll tell you a little bit about how one can mitigate cache attacks with a fully associative randomized cache, or Mirage. This work was published during my PhD in Usenix Security 2021. This was jointly done with me and my advisor at Georgia Tech. So the structure of the talk is like the first and major part of the talk is on Mirage and how it works. And the latter half talks a little bit about how we modeled Mirage and some of the performance results in FireSim versus other simulators and some of the pitfalls in modeling of Mirage itself. So this latter half is more on the modeling aspects. Okay. So why do we need caches, right? You all know that accessing DRAM is extremely slow. And so caches allow fast access to cache data and help improve performance. But this also leads to timing difference based on whether your data is sitting in the cache versus it's absent from the cache. And this timing difference can be exploited with this problem called timing cache side channels or just cache side channels. Why is this a problem? Well, a spy process now has a primitive to learn which addresses are present or absent in the cache. This cache itself is shared between multiple cores, multiple users, multiple processors. And you could have a victim process that is sharing a cache set with a spy process in the same cache. And so these two processes can now conflict for the limited space inside of a set and evict each other's addresses from the set. And using this, a spy process can learn which addresses are being accessed by the victim process in a very fine-grained manner. Let's take a simple example of the prime and probe attack, which first has a spy process filling the cache set with its own addresses. Then it allows the victim to execute and insert certain addresses that are secret dependent into the cache that evicts some of the spy's addresses. And then the spy, by observing or timing the access for one of its addresses and observing a slow access, can learn that the victim process accessed that set. And it can also learn which address the victim accessed, because there is a deterministic relation between addresses and cache sets. With this, there have been several attacks that have shown you can, a spy process can learn sensitive keys. It can fingerprint websites that are being browsed by a victim process. And it can also learn important details about maybe an ML model that the victim is computing on. So this is a very fine-grained source of information leakage through the cache. And the root cause or the key requirement for this kind of information leakage is the incidence of set conflicts, right? The act of a victim address evicting one of the spy's address from the cache. And to observe a set conflict deterministically, the spy process needs a set of addresses that fully fill a cache set. This is also called an eviction set. We'll see why this is important in a couple of slides. Now, there have been a lot of defenses that have tried to prevent this form of information leakage. A classic example is partitioning of cache or partition cache. In this defense, the key idea is to isolate the cache across different processes so that there is no incidence of set conflict, right? They're not sharing the cache set. So a victim address cannot evict a spy's address and vice versa. This is great principled security, but it's also limited in terms of its scalability or practicality. Because if you want to say cut the cache along the ways, there are only about so many ways, right? 8 or 16 ways in the cache. So you can only get about 8 or 16 partitions simultaneously. And as you would imagine, there are easily more than 8 or 16 processes that would run on the same system, right? So this has limitations in terms of scalability. The other paradigm of defenses in cache side channels is randomization. Here, the key idea is to use a randomizing function that maps addresses to cache sets that obfuscates the pattern of set conflicts between different processes. So while the adversary might observe set conflicts, they can't learn anything, or they can't learn anything about the victim address that caused a set conflict. While this is practical to implement because it just requires changing the indexing function inside the cache, there has been a problem that successive randomized cache defenses have gotten broken in a matter of months after they were proposed. So the key question we asked is, can we even design a principled randomization-based defense that can eliminate these kinds of attacks, and that might be resilient to future attacks? To answer this question, we tried to analyze why prior defenses kept getting broken. So the process started with the Intel proprietary cache, which had a proprietary fixed mapping, a linear mapping. And that particular cache got broken by a paper in 2015 that constructed eviction sets in order of n square accesses for a cache with n lines. What this means is, for a typical cache in your processor, you can construct an eviction set in order of minutes or seconds and have a working cache side channel attack. Subsequently, there was a proposal on randomizing these mappings, right? Address to set mappings using a cipher, and to dynamically change this mapping by rekeying. What this means is that before an adversary can discover an eviction set in order of n square accesses, the mapping changes, and so the adversary is defeated, right? This worked to prevent the prior attack. Subsequently, a new attack came out, which optimized this process and discovered an eviction set in order of n accesses. What this means is, before the mapping changes, the eviction set gets constructed and the attack succeeds. Subsequently, new defenses used randomization and also skewed associativity. The idea here was to not just use one randomizing function, but use multiple randomizing functions and pick between them probabilistically. This increased the randomization space for the addresses and made attacks in order of n accesses extremely hard. The search space just increased, right? But with this probabilistic defense, there were new probabilistic attacks, which said, well, we can still construct an eviction set that will not deterministically evict the address, but probabilistically evict it with a reasonably high probability. That still succeeded in order of n access. So try a few times and it still works. The key reason why all of these defenses kept getting broken is because they randomized the locations, but they still continue to have set conflicts at few obfuscated locations. So an attacker, an intelligent attacker, needs to come up with a new algorithm to reverse engineer these locations. And if you can reverse engineer these locations of set conflicts, you can launch an attack, right? So our goal was to not just obfuscate these locations of set conflicts, but eliminate them, right? If there are no set conflicts, you cannot have a set conflict-based attack. So our abstraction that we desired to provide with our cache was that of a fully associative randomized cache. When a line is installed, a random line gets evicted from the entire cache. This does not have any set conflicts, has very principled security. However, there's a challenge, right? As you would imagine, if you wanted to have a fully associative last level cache with hundreds of thousands of lines, when a new line is accessed, when a cache access happens, you have to now search through all of the hundreds of thousands of lines. So lookup requires searching through all the lines in the cache. And this means now that lookup can have impractical latency and power. It might be even slower than just going to DRAM, right? So Clearly, fully associative lookups are a big challenge. But how? So traditionally, we have set associative lookups, right? Where when you have a cache access, line maps to few finite locations, and it's either present or absent in those finite locations within a set. So how do we get the security of a fully associative cache, but retain the lookup complexity of a set associative cache? Security of a fully associative design, but the practicality of a set associative cache. Well, to understand how to get that, we try to leverage insights from modeling of the cache in the form of a classic bucket and balls problem from statistics. Here, we took a cache with sets of W capacity and modeled them as buckets of W capacity. Each bucket corresponds to a set, and the balls inside these buckets correspond to cache lines, right? So you have W ways in the cache set. Similarly, you can store W balls inside a bucket. When you install a ball, you also need to remove a ball from the same bucket. This is similar to when you install a line into the cache set, you also need to evict a line from the same cache set, right? So these bucket overflows are nothing but set associative evictions because they leak which bucket the overflow is occurring from, right? If you observe which bucket you remove the ball from, that means you know which bucket the ball was installed in. So you can learn which address was installed based on observing this kind of overflow. Ideally, we would want to eliminate these bucket overflows altogether, right? So let's see how we do it. Take, for instance, a simple setting where you throw 16 balls randomly in buckets of 4 capacity, 4 buckets of 4 capacity. Of course, you're going to have a bucket overflow or a set associative eviction on each ball throw, right? Now, what if we double the bucket capacity, but still stored the same number of balls in it, right? So throw 16 balls in buckets of 8 capacity. Of course, now you will not see, you don't need to see bucket overflows because there is extra capacity in each bucket. But now when you install a ball, you need to remove a ball. So you can remove a ball from any one of the buckets in a globally random manner, right? So this is what we call global evictions. These don't leak any information, right? So doubling the size of each bucket can help reduce the bucket overflows. But there can still be skews in distribution of balls in buckets, right? If you throw randomly, some buckets might indeed have all of the balls, all of the capacity inside that bucket filled. So the probability of bucket overflow is reduced, but it is still possible. What we observe is that, well, now instead of just using one random bucket, what if you use 2 random choices for buckets and always picked the bucket with the lower load for the bucket where you install the ball? What happens is that you end up with a very uniform distribution of balls and buckets. Like the skews in these bucket distributions are extremely minimized, and you will never get a bucket overflow. All removals of balls continue to be global evictions, like from among all of the buckets, all of the balls in buckets. This basically, so this is a kind of hashing that was studied by Mitzenmacher in 1996, and it's called the power of 2 choices. And what he observed was that, well, if you have sufficient capacity of over-provisioning in each bucket and have this power of 2 choices, your bucket overflows can be almost improbable in the lifetime of the universe. To see how much we need to over-provision our buckets in the case of our cache, we modeled this in a simulator where on the, so the XY plot here on the x-axis shows buckets with increasing capacity, right? We took a bucket with default capacity 8, and then we, added the extra capacity, increase the amount of over provision. And on the y-axis, we show what is the frequency of these bucket overflows. How many ball throws do you need before you get a bucket overflow? And what you'll see here is that with each unit increase in the bucket capacity, the number of balls you need to throw squares. So within 5 to 6 squarings, you reach an insanely high number of balls that you need to throw, about 10 power 34 balls that you need to throw before you get a bucket overflow, if you have 75% extra capacity in each bucket. Now, what does this buckets mean for caches, right? We care about caches. Well, in our cache parlance, what this means is that if you over-provision each cache set with 75% extra capacity and have the power of 2 choices indexing, you can get extremely strong guarantees, which is 1 set conflict every 10 power 34 cache installs, which is, if in terms of time, that's longer than the universe lifetime. Right? So this is the security guarantee that we aim for. How do we practically implement it? Right? In Mirage, which is the cache design that incorporates these primitives, we observe that, well, provisioning extra capacity in the data store is expensive, but provisioning extra capacity in the tag store is not, right? And for placement of lines, we really care about the tag store design. In conventional caches, these are one-to-one. There's a one-to-one mapping between tag and data. So we say, well, let's dissociate them and have only over provisioning of the tags and associate tags with arbitrary data entries using pointers. Subsequently, now each set has extra invalid tags, right? To ensure when a new line is installed, if it finds an invalid tag in its index set, it will always evict a random entry from the entire data store, right? It will evict a random line from the entire cache. To ensure that there is availability of invalid tags in the index set, we use power of 2 choices indexing, where we split the tag store into 2 structures or SKUs. And when a new line comes in, it gets indexed into 2 sets. And we always pick the set with the lower load. This leads to a very balanced distribution of tags in the sets and guarantees the availability of invalid tags in index sets and guarantees global evictions. With this, we get the security guarantee that with 75% extra tags, around 20% extra storage, set associative evictions that leak information never occur in the lifetime of the system. For understanding the impact of performance, we modeled this in a trace-based simulator and compared it with prior defense scatter cache that got broken by a new attack. And on the y-axis, we show normalized performance. And on average, Mirage incurs about a 2% slowdown across a bunch of workloads, which is similar to scatter cache, which also incurs about 1.7% slowdown. We also implemented this on a trace-based simulator, but we also implemented this on more realistic platforms like FireSim. The challenge we had with FireSim was that as of 2020, while FireSim modeled the tag store, so FireSim models the last level cache, right? But for the last level cache, it only models the tag store and doesn't explicitly model the data store. It functionally models the data store by stalling the timing model and going while the request actually goes and fetches the data from the host DRAM. And then once the data is back, it allows the simulation to proceed. So without an explicit data store, it's hard to model the global evictions in Mirage and the pointer based in direction between the tag store and data store. So to functionally model at least the performance impact, what we did is we didn't implement the global eviction part, but implemented the evictions in a randomized manner using randomized indexing, and also increase the cache latency. The effect of this was that, well, the eviction profile in expectation was similar to what you would expect in Mirage, and also the latency to access the cache was similar to Mirage. And with this, while we could, so with this, we've got the opportunity to actually run longer running workloads, entire workloads, and observe that the overall slowdown is not high, right? Even if you increase the latency anywhere between 3 to 6 cycles, we observe minimal slowdown less than 1%, which is better than what we observed in our trace-based simulations. We also did this evaluation with Gem5, and it was in the similar ballpark. One of the things I would like to highlight is that, modeling of the, so in Mirage, in FireSim, while we didn't model the global evictions, that's okay for performance, but not okay for security, right? You can't, to analyze the security properties, you need to implement the entire parts of all the parts of the cache, right? So one of the pitfalls of inaccurate modeling is that, the security claims wouldn't hold, right? And the reason I bring up is that there was a recent paper that demonstrated set conflicts in Mirage within a few 100,000 cache accesses, and claimed that Mirage is broken. But there are a few pitfalls of not modeling Mirage correctly, right? What we discovered is that, they didn't model the global evictions like similar to our FireSim model. And while that's okay to model the performance, that's not okay to model the security, right? And if you don't model the, what we discovered is that without the global evictions being modeled, the cache can actually store more addresses than its capacity. So you might end up with set conflicts because you're putting more addresses inside the cache, right? So this is not something you should do with, if you incorrectly model Mirage, you will get wrong results and your design will be broken. But also there are some other pitfalls, right? While modeling for performance, we don't care about distributions of tags in the cache itself, but it's very important for security, right? And one of the other pitfalls that this paper encountered was that the initial distribution of tags in the sets was assigned probabilistically. And what that means is that some sets will start as full, right? If you look at the distribution of set occupancy in this histogram, there are some sets that are already full at the beginning of the simulation. So, and to break Mirage, you have to get 2 full sets so that you can get bucket overflows, right? So if you start with a full set, of course, you're going to get bucket overflows. So the right way to do this is to start from a invalid cache and install addresses randomly into the cache, right? And at that point, you get a very different distribution of set occupancy, which is extremely hard to break. And the third thing, when you're modeling a randomized cache, you need to ensure that your cipher is random. If you don't have a random cipher in this implementation, the cipher had a very skewed distribution. And what that meant is that some sets were accessed more often than other sets, which means that, you're going to get set conflicts. If you access one set over and over again, you'll get set conflicts, right? So if you use a right cipher, you really should be accessing all of the sets uniformly. And so what we did is we fixed all of these bugs and you don't have any set conflicts, right? So long story short, the reason I brought this up is it's important to have holistic models in simulators to test the security of these defenses. And we would have loved to have this full implementation in FireSim that would have allowed somebody like these authors to run software, run their attack code in user mode and see if they're getting a set conflict or not, right? Unfortunately, they had to, I can't speak for the authors, but they designed their own implementation in a custom Python simulator, and that led to all of these pitfalls. But long story short, going forward, I would really like feedback from the FireSim community to see if designs like Mirage or even other security sensitive designs can be implemented in FireSim so that others who are trying to design attacks can have good models of defenses that then they can try to break, right? Otherwise, there can be modeling issues. So the takeaways from this presentation are that, well, Mirage is indeed secure. And at a higher level, if you have fully associative caches, one can have security against set associative evictions that give you the guarantee that you will not leak any information by observing the evictions, right? The address information. While there have been several defenses previously that have gotten broken, so far Mirage, I believe, has not been broken. And hopefully, I welcome more works on both attack and defense in this space to pressure test some of the security arguments of Mirage, right? And hopefully FireSim plays a role in some of these attack and defense in the game of attack and defenses. Thanks. Questions?
So focusing on caches, are randomized full cache predictions secure? Like if I just randomly evict, is that a good defense? Is the argument it takes so long to do the same guy again that the probabilistic guys can't get a handle on it? Is that the argument there?
So the argument is twofold, right? I think just using randomization is not enough. So for example, prior works randomize it, but the root cause still existed, right? Like the root cause was set conflicts. And even if your set conflicts are occurring, but it's occurring in an obfuscated manner, you're going to leak information. The takeaway from this work is that if you want to eliminate set conflict-based attacks, you need to eliminate set conflicts, right? And so we provide the abstraction of a fully associative cache and randomization, right? So your evictions are random, yes. They are randomly selected from the entire cache, and there are no set conflicts, right? So that's really the takeaway. If you want to eliminate information leakage, you need to eliminate the source of the information leakage.
So you effectively get random eviction.
Yes. So random fully associative evictions. Yes.
And so that leads kind of my next question. So we've done all this work on like optimizing performance by finding, re-referencing re-reference prediction intervals, Hawkeye, and all that stuff. Are we just gonna surrender that? Is that what we have to trade for security?
That's a great question. And I don't think, so I'm going to have two hats on, right? Like if I'm somebody who is like paranoid about security and I really care about cache side channels, I would say, I don't want these optimizations. Give me a primitive where I can select this primitive where all of these optimizations are turned off that can leak information potentially.
That's your partition.
Yeah. No. Partition caches are even worse, right? Like that's just not going to work.
Sure.
Right? So I think what I'm trying to say is that if you really care about security, there is a performance cost, right? And at that point, I would argue that it's better to turn off intelligent replacement because that can leak information and deal with the performance loss, right? That's one. Second, so there are going to be some people who are paranoid about security to that extent, right? I think there is also a class of people who like security but don't want to pay the cost of it, right? In that, for those kinds of people, I think what you need is a way to turn on these optimizations where it's not going to leak any information and then turn it off only when it's going to leak information, right? So you need a higher level information about what is leaky and what is not. Like, what are your secrets? Can that leak through these cache accesses? And if they can, then should I be turning it off, right? So I think at that point it becomes more nuanced and you need a lot more information than you currently have. But I think that's an open area for research, right? How do you get performance when you don't care about security? And when you care about security, how you turn them off in demand.
last question. Now, you mentioned that the power to skew thing allows you to get away with 75% overhead with tags. If you increase that power, does that reduce the overhead that you get?
That's a very good question, right? So the question basically is if you don't restrict yourself to power of 2, but say power of 3 or power of 4, right? So the answer is the returns are diminishing, right? So you get the biggest bang of buck with 2, going from 1 choice to 2, because the average load on your buckets with 1 choice is approximately log of n, right? When you have like n balls that you're throwing in. When you go to 2 choices, it becomes log n. So that's a dramatic reduction in the load. Going to say 3 choices doesn't give you that much benefit, because at that point you're already like your skews are very close to 0, right? So it doesn't help as much. We have some in the paper. We have some ideas to reduce it from 75% to 50% by combining power of 2 choices with cuckoo hashing. And so I can point you to that. But I think, again, that is again an open area of work, because the guarantees are extremely strong at some costs. It's an open area to figure out how to reduce these costs while keeping the guarantees reasonably high. Right. So, yeah.
Quick last question that's on slide.
What I understood is that you implemented Mirage for your Usenix publication. Was there a reason that the implementation was not open source so that others could use a more realistic model for follow-up work?
It is open source. It's available on GitHub and implemented in Gem 5. So if you can go download it, run it. Yep. It's been open source since 2021.
Thank you.
Awesome. Thanks, Gururaj.
Okay, thanks. And yeah, well, the link is on my on the slide as well. So, yeah. All right. Thank you so much.
Thank you.